In this video tutorial, we're going to begin looking at how we can estimate the construction and installation costs for wind turbines and wind farms, and we're also going to look at some of the different methods of generating income from a wind farm. So first of all, we'll look at an overview of the different costs associated with constructing a wind farm, and then we're going to make a cost approximation based on a wind farm with a 20 megawatt average output. We'll then look at some of the different types of income, and again we'll make an approximation about how much income our 20 megawatt installation is going to generate. And finally, we'll look at the break-even point and future profits. So first of all, it's important to understand that there's a number of different costs associated with constructing a wind farm. First of all, we have planning and feasibility costs. Identifying a potential site is only the first step because we need to collect resource data, we need to engage in discussions with landowners, and we need to carry out environmental impact assessments before we can even begin constructing the wind farm. In terms of construction, we have costs for civil works, and this is things like foundations to mount the wind turbines on. But for an onshore installation, this is also going to include things such as haul roads and hard standings for cranes. So there's lots of civil works that need to be done before the wind turbine itself can be constructed. We then have any costs associated with upgrading the network and running cables to and from the turbines and to the grid. And finally, we have the cost of the turbine itself. And data suggests that the cost of the turbine amounts to approximately 70% of the overall cost. One of the things that should be evident is that there's a huge amount of variability in what the overall cost for a wind farm could be. There's lots of different elements, and these elements can vary from project to project. So all we can do in order to make a relatively realistic approximation is to look at average data. So we're going to make a cost approximation for a 20 megawatt average output installation, and we're going to do that by looking at average data. Now, one important thing to point out is what we're looking at here is a 20 megawatt average output installation. Now, we know from earlier tutorials that wind farms are normally sized according to capacity, but that's less of a reliable measure if we want to compare different types of renewable energy against each other. So we're going to look at average output, which means we need to take into consideration the capacity of the wind farm, but also the capacity factor. So the first source of information that we're going to use to make an approximation on the cost of our wind farm comes from the local government association. Now there's some information above the table there. It says some typical figures for the installed cost for different scales of wind turbines are provided in the following table. So we see on the left hand side we have different sizes of turbines along with the capital cost for the turbine, or the initial cost. It says capital cost figures are approximate and include installation costs due to civil works. Planning and feasibility costs are not included as these vary considerably. Now the other thing that's worthy of note is that this data comes from 2009 figures, and as we'll see later on, the cost of turbines is probably lower than the cost of turbines from 2009, and we'll look at the reasons behind that later. But using the data we have, we can see that the larger wind turbines range between 1 and 2.5 megawatts capacity. Now we need to approximate the cost of a wind farm with an average power output of 20 megawatts. So the first stage of our approximation is to incorporate the capacity factors that we saw in an earlier tutorial. If a wind farm produced rated power 100% of the time, then its capacity factor would be 1. But we know that a wind farm, on average, will produce 30% of its rated power. That's why we're dividing the 20 megawatts that we desire for average output by the capacity factor. Now what this is telling us is that we need a wind farm with a capacity of 67 megawatts in order to produce an average of 20 megawatts. So the rated capacity is roughly 3 times higher than the average output, as we would expect with a 30% capacity factor. So there's a number of different ways we can make up 67 megawatts. One way would be to use 67 1 megawatt wind turbines. Well, from our table here, we know that large wind turbines range from 1 megawatt to 2.5 megawatts according to this data, Therefore, the smaller wind turbines are going to be £2 million. So for our approximation, we have 67 1 megawatt wind turbines at 2 million each. 67 times 2 gives us 134 million. Therefore, to build a wind farm with a capacity of 67 megawatts, we need 67 1 megawatt turbines at £2 million each. Let's look at the other end of that bracket though. So if we want to construct our wind farm using 2.5 megawatt wind turbines, then we're going to need 27 turbines. The reason being is 27 times 2.5 gives us our capacity. So now we need 27 of the larger wind turbines, and the larger wind turbines are 3.3 million each. 27 times 3.3 gives us 89 million. So based on this information, we can see a huge economy of scale. We can see that using the 2.5 megawatt wind turbines is likely to be considerably cheaper than using the 1 megawatt wind turbines. This would also be indicated in the end column here where it says simple payback period. We see that it's only the larger wind turbines that are likely to cover the initial costs over their life cycle. So the payback period on the capital cost is 8 to 15 years for a 20 to 50 kilowatt wind turbine, but it's only the larger wind turbines where we see a much shorter payback period. But the sensible thing to do again is to take the average of those two costs, which gives us an average of 112 million. And that's for the full wind farm with a capacity of 67 megawatts, likely to produce an average of 20 megawatts. Okay, let's repeat that process with another set of data, just to make sure we're happy with our estimates. And the data we have here is from a company called Renewables First, and they're a consultant to the renewables industry. So again, we have some maximum power output turbines, meaning rated power, and we have some equivalent costs. And underneath we see, for reference, typically the actual wind turbine costs around 69% of the total project cost, and this is linked to the fact that the costs indicated here are the project cost. So that would include our civil works and our cabling costs and so on. So, once again, we want a 20 megawatt average output. Therefore, we need a wind farm with a capacity of 67 megawatts. Again, we're going to use the larger wind turbines. So if we use the 1.5 megawatt wind turbines here on the second row from the bottom, they have a cost of 2.7 million each. Well, in order to reach our 67 megawatt capacity, we would need 45 of those turbines. And 45 turbines at 2.7 million each comes to a total cost of £122 million. But let's look at another alternative, and this time we're going to use the bottom row, the Enercon E82. So we can see that the Enercon E82 wind turbine has a power output between 2 and 3 megawatts capacity. So if we take the average of those, 2.5 megawatt, we would need 27 of those turbines in order to achieve our capacity of 67 megawatts. 27 turbines at 3.1 million each gives us £84 million. So once again we see that economy of scale where the larger wind turbines lead to a lower project cost. And finally, let's take the average of those two values, giving us an average of 103 million. So the likely project costs here are going to be around £100 million for simplicity. And we've used two credible sources in order to establish our estimates. So now that we've looked at the costs associated with constructing a wind farm, let's look at the likely income. Now, there's a number of different sources of income, and we'll go through each of these in turn. The first is something called feed-in tariffs. Now, feed-in tariffs are normally only paid on small installations up to 5 megawatts, so we won't be entitled to that for our given example here. But things such as solar panels on domestic premises or small-scale wind turbines would be entitled to claim the feed-in tariff. We then have the export value of the energy. So if we produce the energy and then we sell it to a supplier, then this is the value that we're likely to achieve for the sale of that electricity. Now this is a little bit more complex, so let's have a look at a couple of diagrams. Now when companies generate electricity, they sell that in the marketplace. And they sell that in a number of different ways, where suppliers would bid on the electricity and then negotiate on prices. But the other thing that's important to point out with that model is that it's affected by demand. If demand increases, wholesale price increases. If demand reduces, wholesale price reduces. And suppliers will be bidding on this electricity at different times throughout the day, different days of the week and different months of the year. So the wholesale price of electricity is very volatile. We see just in 1 week here, lows of around £52 per megawatt hour and highs of around £71 per megawatt hour. So there's a huge amount of volatility in the market. And these are daily averages. If we were to look at, say, hourly averages, then the spikes would be much higher. There's also different ways that energy suppliers can bid on the cost of this electricity. We can hold auctions, and we also have here spot prices, which is one-off prices or one-off deals. Some suppliers will pay for electricity years in advance, and others will pay on a day-to-day basis. So once again, it's important to point out that the wholesale price is very volatile. We see another slide that demonstrates this, going from 2010 to 2018, and the dashed line represents the average wholesale price. Our equivalent scale on the right-hand side again is pounds per megawatt hour, and we see throughout that life cycle huge fluctuations in the wholesale price, dropping as low as £35 in April 2016 and peaking at around £56 per megawatt hour in both 2016 and 2018. So it's quite an unpredictable measure. Now, the other type of income is called offset value. And if an energy company both produces or generates and sells or supplies electricity, then they can offset what they purchase in the wholesale market. So as we've seen in the wholesale market, prices are very volatile. If a company also generates electricity, then they can offset what they purchase in that volatile wholesale market. They can basically choose their timing to get better prices. Okay, so let's look at an income approximation for our 20 megawatt installation. Now once again, the data we're looking at is from renewables first. And what we see is the export price for electricity is fixed at around 5p per kilowatt hour. That would be the same as £50 per megawatt hour. So we can compare that to the previous graphs, an average of around £50 per megawatt hour. We also see reference to the feed-in tariffs, but as mentioned before, feed-in tariffs are only available for installations up to 5 megawatts. So based on this, we would have to assume that we could only achieve 5p per kilowatt hour. However, the data that we're looking at here was correct from November 2016, and we have seen a slight increase in the export prices of electricity. Now, all of this said, we're going to use export price or export income as our measure of income, but we've already said that there's likely to be additional benefits associated with the offset income. And in the next tutorial, we're going to look at some additional benefits. So although we're looking at the export price or the export income as our measure, this isn't the only source of income, and we wouldn't actually be capped at 5p per kilowatt hour of energy we produced. But it's useful as a benchmark. So, to begin, we've said that our wind farm needs to produce 20 megawatts of actual power output. The important thing here is this is power output, whereas these values are measures of energy. The difference being power is energy per second, whereas energy is a total quantity. So our wind farm is going to produce 20 megawatts of power, and 20 megawatts of power is the same as 20 megajoules every single second. So, if we're producing 20 megawatts every single second, then we times it by 60, and that will give us the amount of energy every minute. We times it by 60 again, and that will give us the amount of energy every hour. We times it by 24, and that will give us the amount of energy every day. And then we times it by 365, the days in a year, and that will give us the amount of energy in a year. And I've got the calculated value there, megajoules per year. The reason it's megajoules is because our initial value here was in megawatts. I'll just go through that again. 20 megawatts is 20 megajoules per second. Times 60 gives us megajoules per minute. Times 60 gives us megajoules per hour. Times 24 gives us megajoules per day. And times 365 gives us megajoules per year. So what we're going to work out is how much income we get per year. The problem here is our units differ. Here we have energy in megajoules per year, and here we have energy in kilowatt hours. So let's convert 6.31 times 10 to the 8 megajoules into kilowatt hours. Well, the way that we do that is we take our quantity of energy, we divide it by 60, and we divide it by 60 again. This is basically the number of seconds in an hour. Divide by 60, divide by 60. Or we could just divide by 3,600. The key is that this division here is the number of seconds in an hour. The reason we need seconds in an hour is because here we have kilowatt hours. So doing that, I get 175,200 megawatt hours. It's megawatt hours because our energy was measured in megawatts. All we've done is convert from seconds to hours. So the final step to get from megawatt hours to kilowatt hours is to times by 1,000. Timesing by 1,000 gives us 175,200,000 kilowatt hours. And for each of those kilowatt hours, we're going to get paid 5 pence. However, as mentioned, I'm going to use 6 pence because this value here is a little bit outdated. So using 6 pence, I've got my 175,200,000 times 6p gives me 10.5 million. And that's 10.5 million pounds per year. And we'll see how that impacts later on. But please remember, I've used the export price or the export income as a measure, but in actual fact, the income per kilowatt hour would be higher than the 6 pence that I've used here. And we'll explore the reasons behind that later on. Now, we can refer back to our local government association data here because in the simple payback period, we saw indications of how long it was likely to take for a wind turbine to pay for itself. Now, we was working in this row here where it says the capital cost should be repaid in 1 to 5 years, but we've seen the average cost of our wind farm is around 100 million and our income per year is 10 million. So in actual fact, based on our evidence or based on our calculations, the payback period would be closer to 10 years. That said, the income from our wind farm is likely to be higher, and as mentioned, we'll explore the reasons behind that in a later tutorial. So to summarise, we've looked at some of the different costs associated with building a wind farm, and we made an approximation of the cost of our 20 megawatt average output installation. We looked at some of the sources of income, and we made an approximation on how much income our 20 megawatt installation was likely to produce. We did make some assumptions there, because first of all we assumed that we would be exporting our electricity, and we also used the relatively low export prices in order to carry out our approximations. But what we found was that the break-even point for our installation was somewhere in the order of 10 years. We had an installation cost of 100 million and an income of 10 million per year. In terms of future profits, our installation is still likely to produce 10.5 million per year as a minimum, after the 10-year period of covering our initial costs.